Good day, Bayaws! Welcome back to our YouTube channel, Bayaw Tutorial. In this video, we are going to solve a problem from thermodynamics and heat transfer that involves the vapor and power cycle. So here is our problem. The compression ratio of an ideal Otto cycle using argon as the working fluid is 10. The minimum and maximum temperatures in the cycle is 450 degree Rankine and 2500 degree Rankine. The quantity of heat transferred to the argon during the heat addition process, as well as the thermal efficiency and thermal efficiency of a Carnot cycle operating between the same temperature limitation must be calculated. So here are the given and diagram in this problem. So we have the PV diagram. At state 2 to 3, we have Q in, and at state 4 to 1 is Q out. So we have assumption in this problem. First is the air standard assumptions are applicable with argon as the kinetic and potential energy changes are negligible, and argon is an ideal gas with constant specific heat. So since we are dealing an ideal Otto cycle in this problem, it has 4 processes. The 1 to 2 process is isentropic compression, where the entropy is constant. The process 2 to 3 is the constant volume heat addition, that's why there's a Q in. The process 3 to 4 is a isentropic expansion process with which the entropy is also constant, and 4 to 1 is a constant volume heat rejection. So let's proceed. At process 1 to 2, a isentropic compression, we need to identify first the temperature at state 2 because the temperature at state 1 is already given. So using this equation, we get the value of 450 degree Rankine as the value of our T sub 1 times 10, the value of our compression ratio. V sub 1 over V sub 2 is equals to compression ratio. Raised to the power of 1.667 minus 1 is equals to 2090.32 degree Rankine. Next is process 2 to 3 at constant volume heat addition, where the Qn is equals to the specific internal energy at state 3 minus the specific internal energy at state 2. And Qin is also equals to constant volume times temperature at state 3 minus temperature at state 2. Since we have the value for these given quantities, by substituting it, we have 0.0756 BTU over LBM, or pound mass per degree Rankine, is the value for our constant volume, times the difference of 250 and 2090.32 degree Rankine is equals to 30.97 BTU per pound mass. Next is process 3 to 4, where is the process of isentropic expansion. Since we have the value for our T3, we need to identify the value for our T4. So 2500 degree Rankine multiplied by 1 divided by 10 raised to the power of 1.667 minus 1 is equals to 538.20 degree Rankine. So next is process 4 to 1, where the constant volume heat rejection. So we have Q out here. So Q out is equals to the constant volume times the difference of temperature at state 4 and temperature at state 1. So by substituting all the given values, we have 0.0756 BTU per pound mass degree Rankine multiplied by the difference of 538.20 and 450 degree Rankine And by equating or simplifying this equation, we can get the value of 6.67 BTU per pound mass. Now that we have the value of our Q in and our Q out, we can now solve for the thermal efficiency. So the thermal efficiency is equals to 1 minus Q out divided by Qn. So 1 minus 6.67 BTU per pound mass divided by 30.97 BTU pound mass, crash out the same unit, is equals to 0.78. And since it is the thermal energy, we need to convert it into percent. So we need to multiply it by 10, so it is equals to 78%. Next is the thermal efficiency of a Carnot cycle operating between the same temperature limitations. So we have the thermal efficiency of Carnot cycle is equals to 1 minus the temperature minimum divided by temperature maximum. Since temperature minimum is equals to 450 Rankine and the temperature maximum is 2500 degree Rankine. So 1 minus 450 degree Rankine divided by 250 degree Rankine is equals to 0.82 times 100 is equals to 82 degrees Celsius. So the results in this problem, since we are asked to calculate the quantity of heat transfer to the argon during the heat addition process, or the Qn, and the thermal efficiency of Carnot cycle operating between the same temperature. So here's the result for this problem.